This meeting is being recorded.
This next section is a review of polar covalent bonds and, in general, electronegativity and how to determine whether or not a bond is classified as covalent and more specifically as polar covalent, or would it be considered an ionic bond? So if you recall, this is a table here showing different electronegativity values, and we see that fluorine is the most electronegative atom, right? It has the highest value here, and everything else is, relative to fluorine being 4.0. So we can see oxygen's right next door. That is about 3.5, and it goes down as we get further and further from fluorine. So the general trend is, if you see these increasing lines, they increase in this way. So from the bottom left to the top right. So you can always gain, relative electronegativity values for atoms in the same column or the same row of, this is abbreviation for the periodic table of elements. So even if you don't know exact values, you can always make some generalizations. Um, but to determine whether or not something is a bond that's considered covalent, polar covalent, or ionic, you would need to have specific values. You actually subtract or one value from the other to find the difference, right? The delta En, the difference in electronegativity between the two atoms. So things like a carbon-carbon bond, these will be zero, right? No difference. And then these would be considered, is that greater than or less than, right? 0.5 for carbon-hydrogen bond. So that these would be considered strictly covalent, not really polar at all. So once we get higher than that 0.5 threshold up to about 1.7, we see a polar covalent bond arise. So something like carbon bonded to oxygen would experience what's called like a dipole moment here, where we have two different poles. We have a positive pole and a negative pole, and these lowercase deltas here, this little d like this, is showing us that we have a partial positive, and then over here we have a partial negative charge. So that's designated with that lowercase delta there. And then we have the more extreme ionic bond. So any difference in electronegativity, right? So delta En, that is greater than 1.7. This would be an ionic bond. So the different types of bonds here, if you know that a carbon-oxygen bond would have this polar covalent designation, that will help us to explain certain types of reactions where one side of the molecule gets attacked or forms a bond with something else due to this difference in charge or this dipole that results. And then also reagents or reactants, such like sodium hydroxide here, we know that these would be, in solution, these would be ionic, right? These would exist as sodium cations and hydroxide anions. So knowing different types of bonds and general trends, just based on differences in electronegativity. For instance, here we have carbon-oxygen is generally a polar covalent difference in electronegativity, whereas carbon and lithium over here, their difference in electronegativity is so great that they are considered ionic. So this larger difference, right, gives us these ionic compounds like the salts, like sodium chloride, sodium fluoride, etc. And then the smaller differences over here, right, these would give us our covalent bonds. And then somewhere in between, we have those polar covalent, right, in the middle. So the last slide here in this section shows us that sometimes when molecules are on the edge of electronegativity differences, so this one here between carbon and lithium is noted to be about 1.5. So it's right on the cusp. So it's right between being polar covalent and ionic. So Sometimes you may see it drawn more as a molecular compound and then more as an ionic compound, depending on some other conditions or even from textbook to textbook. So, this absolute term of electronegativity difference, they note just take that lightly. It's just more of a trend or generalization that can be made than, an absolute value. All right, so that's everything for this section. We will continue with 1.6 next time.